Okay, so welcome everybody. It's a real pleasure for me to introduce today the talk by Alex Fullerton. At present, he is staff researcher and chair of the executive committee of the science staff at the Space Telescope Science Institute. He obtained his PhD in the University of Toronto in 1990, and after that he was a postdoc in the Bartle Research Institute of the University of Delaware and also in the Universität Sternwarte München in Germany. During the last 15 years, his career has been deeply involved or connected with two space missions. One of them is FUSE, the Far Ultraviolet Spectroscopic Explorer, and more recently with the James Webb Space Telescope. He was support astronomer for the FUSE mission and also instrument scientist and branch manager for the near-infrared imager and slitless spectrograph for the James Webb. His main research interests are connected with hot massive stars, especially with those aspects related to variability, stellar winds, and magnetic field. And from what I've seen in the massive star conferences, Alex is a really good speaker, so I'm sure you will enjoy very much the talk he's going to deliver today. So, thanks.
Thank you, Sergio. It is a great pleasure to be in Tenerife after many years, but I'm also aware that we're very close to Carnival, and so I thought that we would have an easy day today, not so much physics, and instead we'll have a bit of a historical tour from my own personal perspective about the development of the field that has occupied me for most of my career, and this is the development of structure in the winds of hot massive stars. So I'm going to take you on a historical tour that will be, I hope, a little bit of fun and not too heavy for today. So I want to talk about an observation of theory, some small things, some big things, and then where we are today. And this is highly personal. Other people would give a different talk. So, Chapter 1, an observation and a theory. So, in the 1960s, before I was really cognizant of astrophysics, O-stars were very simple and kind of boring things. They were luminous, they were massive, they were hot, we knew that. Their atmospheres were in radiative equilibrium, and we knew there was a high binary fraction. Apart from that, the only thing they were good for was exciting H2 regions and making beautiful pictures for us. And so strong spheres around hot stars. All that changed in a very big way in 1965. When this young man, Don Morton from Princeton University, launched a Araby rocket and got ultraviolet spectra for the first time of the stars in Orion. Actually, the very first time his rocket crashed, the parachute failed, and the camera and everything was destroyed. So the second time he got some spectra of Zeta Orionis, the easternmost star in the belt of Orion. Those of you who've been around long enough can recognize that in this photograph here, there's an absorption and an emission. The rest of us are more used to looking at traces. And here's the very first spectrum of an O-star in the ultraviolet. And you see there are these P Cygni profiles, which we'll talk about a lot more soon. But they're, suffice it to say for right now, that they're signatures of mass loss. We know that because we see them in nova after an eruption event. So Don was actually an interstellar medium person, and he very quickly estimated the column densities and found out that the mass loss rate implied by these P Cygni profiles was about 1 × 10⁻⁶ of a solar mass per year, which is actually quite a lot. The sun is 10⁻13 solar masses per year. So this actually changed our view of hot stars completely. Instead of just putting out ionizing radiation, they're streaming out matter as well, which affects the evolution of the star over the course of its several million year lifetime, And it also affects their surrounding by returning energy, momentum, and possibly chemically enriched material to the interstellar environment. So feedback was born in 1965. Well, obviously this observation called out for a theory, and a theory came along very quickly by Leon Lucy and Phil Solomon, who recognized that the resonance lines in the spectrum, the very same lines potentially that showed the P Cygni profiles, can absorb momentum and therefore drive an outflow. So their first paper came along just a few years after the observation. So something needed to be explained, and a theory came along. However, the standard theory really started a couple years later. This is one of the theories that is so well known that it's known by the name of the authors on the paper, Castor, Abbott, and Klein, taken at different epochs, actually, those pictures. The CAK theory. And what they also used was the resonance lines, we'll talk about that in a minute, to drive the outflow, but they recognized, whoops, there we go. Now we've gone. There we go. They recognized that that the radiative transfer depends sensitively on the local velocity gradient. This is essentially the Sobolev approximation. And that was the key part of driving mass loss rates of 6 times 10 to the minus 6 solar masses per year. And they also found that static models for these stars simply don't exist, which is also what the observations were telling us. If one random O star has a mass outflow, then probably all of them do. And that has been borne out over time. The next set of developments started in 1986, a few years later, with another paper known only by its initials, Poldrack, Puls, and Kudrytsky, PPK, and they took the Castor, Abbott, and Klein theory and have modified it almost continuously over the years, so that it is a very refined and elegant theory of radiative transfer now. There's nothing elegant about my talk today, so I won't go into the details of that, particularly with Puls sitting here. He can do it better than I can. But I wanted to tell you just very quickly about the physical underpinning of the theory. So the idea is that you have a metal ion, maybe iron 5 or iron 6 or nickel 4. It absorbs momentum from the radiation field of the star. An ultraviolet photon comes in and it absorbs h nu over c in momentum. So that gives it a little push. But this is a resonance line. So it essentially scatters. So the electron is promoted, and almost immediately it de-excites, and the photon goes off in some other direction. So it loses some momentum. So the net momentum gain depends on this total interaction here. However, since the scattering process is fore-aft symmetric, on average, the cos theta term for the loss is 0 on average. And so on average, there's a net radial transfer of momentum to this single ion. The metal ions, they're ionized, so they drag along the hydrogen helium with them. And that's how the wind gets going. So we think about the interactions coming through the line profile. Here's a picture of a line profile that's being accelerated out in velocity. And this is like a Doppler profile, something like that. So the photon comes in at one side, at the blue side of the line profile. It might scatter many times in here, but eventually it's going to find its way out. And then it will sail clear through the wind. It will interact. Really, the net interaction will be an absorption here and a scattering out here. So, and whatever happens in here doesn't really matter. So, and once it's free, it'll fly freely to infinity. So the absorption happens. The scattering happens in this way. It gives it a little push where a new photon can interact with it. Gives a little push, and so on as you go out through the wind. here you see immediately why the velocity gradient is important, because if you tip this up a little bit, you'll see you have a fresh supply of photons that can push a little harder. And if you, conversely, if you tip the line down, you would lose that driving. Even though the momentum transfer per ion is very small, you ultimately sweep out a broad band of radiation, and that is why the mechanism works. So that's just the Doppler, our friend the Doppler effect, sweeping out through the wind and driving it to infinity by carefully adjusting the velocity gradient as it goes. So if the velocity gradient is too steep, it won't work. If it's too shallow, it won't work. If it's just right, you'll drive it to infinity. Our main diagnostics of this are the P Cygni profile. And so I wanted to take a minute just to talk about the P Cygni profile. There's a star sitting in the middle. The theory of Castor, Abbott, and Klein, as modified by Poldak, Pulzin, Kudrytsky, has several main assumptions. The standard model is that it's spherically symmetric, so shells around the star. The wind is monotonically expanding and stationary. It's not a function of time. And so to make further progress, we need to have an observer here. We need to specify an observer. So we'll just pick an observer. We'll call, we could call him anything. Let's call him Sergio. And we'll send him now to several kiloparsecs that way. He's going to paddle, so it might take a while. There he goes. Having specified a direction for an observer, we can now make projected line of sight velocity contours from that monotonically expanding velocity law. And you'll see that some are blue. Those are coming towards the observer Sergio. Some are red, going away. There's a region that is occulted by the star that Sergio can't see. And if we now put down the final assumption is that the wind is homogeneous, so that there's the same number of ions at the same radius everywhere, we can now predict what the P Cygni profile should look like. A couple things can happen. So a photon that was going to Sergio can be scattered out of the line of sight. That will show up as an absorption. In a weak line, it won't be saturated. If there's enough material, it'll be completely saturated. There's nothing coming through. This photon, which was never going to get to Sergio, can be scattered into his line of sight, and that would be a blue-shifted emission. So down here, where B is, so forward scattering. Similarly, down here, this was never going to get to Sergio, except it got backscattered. And now ends up in his line of sight. That's over here. And this one was never going to get to Sergio and is still never going to get to Sergio, so that's just lost. So this is the prediction of the model for a P Cygni profile that's not too strong and one that is very strong. They should look like this. And the whole problem is that they don't look like that. So here are some observations from a long time ago from the first UV observatory, OA03, known as Copernicus, and another paper by Don Morton from 1976 that shows a bunch of weird things. So in the star up top, Zeta Ophiuchi, there are these big dips here that don't show up in the predicted profile, narrow absorption components. Down here, the edge is a little softer. The edge right at the terminal velocity, the maximum velocity of the outflow, is a little softer, not as steep as it should be. And you don't see this stuff here because there's a so-called black trough that all this structure is gone out. So that's what we want to explain. And this tells us immediately in 1976 that the winds were far more complicated than the standard model predicted. So, catch our breath, and now we'll talk about small things for a little while. By small things, I mean small-scale structure. So we're going to try to explain these first few things. Leon Lucy was interested in the X-rays that were observed from these winds. That's a whole separate story. But for reasons we will come to, he thought that there might be non-monotonic velocity structure. So, instead of just one-and-done interaction, the photon can interact here, it can interact here, it can interact here, because the velocity structure is not monotonic. What Leon realized was that at each scattering event, sort of roughly half the photons go forward, or half the light goes forward, and half goes backwards. So if you have enough of these events, so half goes forward, you hit another one, half of that goes on, so now we're at a quarter, hit another one, half of that goes on, now we're at an eighth. If you have enough of these interactions, no light will go forward. And so you will end up with no forward scattered emission, and you will have a black trough. Some other things will happen too. You will have less forward scattered emission here, more back scattered emission here. But this was the initial, you notice from the paper here, this was a long time ago, this was the initial explanation for black troughs. And that has worked out pretty well. This is still the understanding, but what was in the back of Leon's mind at the time, and has been developed much further, is that, that this non-monotonic velocity structure is a consequence of the inherent instability of these hot star winds. So here's Stan Iwaki's diagram again, and we talked about how the line force is just balances and drives the wind to infinity. Now imagine that a tiny piece of material here gets a velocity perturbation. So it's going a little faster than its neighbors, and it steps out into the bright light that's coming from here. So it gets a little more force, so it goes a little faster. So it steps out further, so it gets more light, so it goes faster and faster and faster. So it's unstable, intrinsically unstable to small-scale perturbations. And this realization, this was actually known for a long time, but it took a while before we could calculate the consequences of this. And the consequences are that these winds are incredibly unstable. Here's another paper known by its initials, Iwaki, Castor, and Rybicki, OCR. And they did the first simulations that predict the structure of these disrupted winds, which, nicely enough, produce X-rays, because they produce shocks, and they also produce exactly this kind of non-monotonic velocity structure that you need to explain the black troughs. What happens is that the wind gets overdriven in places, and it crashes into the material ahead of it and then clumps it, compresses it, and on it goes. So this instability drives things to high velocities and also clumps the material. Here's a simulation by Achim Feldmayer that shows how rapidly it grows. This is over the course of a few flow times, the time it takes for a particle to go from the surface of the star out to infinity, or to its terminal velocity anyway. And over a few flow times, you see the structure starting from a stable structure and giving it a little infinitesimal perturbation at the base of the wind. It gets completely disrupted and chopped up. So this is a very, very powerful instability. The consequences are that we can explain the weirdness in the profiles. On the left is an early attempt to look at the soft blue edges. So you see, here's the velocity law from a simulation, or the velocity derived at a snapshot of velocity at a moment in time. The smooth velocity law is the dashed line, and you see that there's this overdriven by the instability velocity peaks. So it's non-monotonic, and there's this small amounts of gas that are driven to extremely high velocities. So the non-monotonic creates the black trough because of the Fabry-Perot effect of just, every time you hit something you lose. You lose more in the forward direction than you gain. It also provides for soft blue edges because there's a small amount of gas driven to much higher than the terminal velocity. So in these early simulations, we didn't quite have enough structure to get down to blackness here. But in later ones, there's more structure here. You'll notice this is actually going out much further into the wind. You get both the black trough and the in this case, very soft blue edge. It's not a sharp, abrupt transition. So these two things are diagnostics. They tell us instantaneously that the winds are more complicated than the standard model tells us. Well, there's another little story that I like to go through because it's really one of the few places that I appear in my own story here. So with the FUSE satellite, my favorite satellite, we were able to access the far ultraviolet below the Lyman alpha line, and that includes a very interesting phosphorus 5 doublet. Phosphorus 5 is very interesting because the abundance doesn't change over time. It only changes when there's a supernova, so for a given O star, it's not going to change. It also is interesting because it's never saturated, because phosphorus is not actually a very abundant ion. So it's perfect for trying to measure column densities and therefore mass loss rates. The prediction was that phosphorus 5 would be a dominant ion somewhere in the O star domain. As an observer, I had no idea where, but we thought that if we observed a full range of O stars, we should have a good mass loss indicator somewhere. So if we compared it with other mass loss indicators, we should have good agreement. So here was our attempt at agreement here, and you see that compared with other mass loss diagnostics like free emission or H-alpha emission, we were off by factors of more than 10, which is a lot. So this was a problem. I thought the problem was entirely due to the fact that these other mass loss diagnostics were biased. They require two particles, an electron and an ion, or an ion of something, to make their radiation, and so they were biased indicators of what was going on. Whereas the UV resonance lines depend only on scattering, they're proportional to density. What could go wrong? So I just thought that these indicators were wrong, basically. And my explanation was the phosphorus 5 has given us the right answer, but no one liked that answer because then the mass loss rates were too small and so on and so forth. So it turned out to be much more subtle and much more interesting as well than just being a biased an indicator of biased diagnostics. So another observation required more theoretical work to develop. This came from Lida Oskanova, Wolf Rainer Hamann, and Achim Feldmayer. What they realized was that when you're talking about resonance lines, there's a lot of absorption power there. And if you're talking about clumps, distribution of material, sorry, I missed one point. The way out of the dilemma was that the biased indicators, the rho squared indicators, were diagnosing clumps of material. They were giving you too high an answer because of the rho squared in a non-homogeneous material. So we immediately knew the winds were clumped. When they're clumped with resonance lines, the resonance lines could become optically thick. And therefore, the radiation transfer changes completely because if you miss a clump, the photon can stream freely without ever interacting with material. Whereas we were assuming that it always had to interact somewhere along the yellow streak there. That's an isovelocity contour. So different transitions can have different optical depths, and you can have different degrees of biasing in your diagnostic. They particularly showed the phosphorus 5 was optically thick to the kinds of clumping, and so as the porosity of the wind, that is the space between the clumps, increases, the net absorption decreases. So we now have a more complicated situation where we have to take into account the optical depth of the different diagnostics that we're using, H-alpha or the phosphorus 5 lines or whatever. So this is now actually, though, a very different conception, a different schematic model for what the wind of the star looks like. It got a little bit worse when Stan Iwaki realized that even if you had spherically symmetric shells, you would lose photons because they can wander in velocity space and leak out that way. So he calls this velocity porosity or veracity. And so there's these two effects that are all working to weaken optically thick absorption lines, which is a great complication. But is also a diagnostic of the fact that there's a lot of structure in the wind that was unknown of earlier. When you put all this together, as Branketzka and John have done with their colleagues, you actually can get close to harmony between all your diagnostics in a self-consistent way. So probably a little hard to see here. The observations for H alpha are dotted or dashed, and the black solid line more or less fits them, and the black solid line more or less fits the phosphorus 5 line. Same deal down here for phosphorus 5 and up here for H alpha. So by taking account of all these things, the mass loss rate comes down, but not as far as Fullerton, Massa, and Prinja said. But we've also got a much more complicated structure of the wind now. So catch our breath for a moment. Here's how the standard model is doing. We know now that the winds are not homogeneous, they're not stationary, and they don't have monotonic velocity laws. We haven't yet addressed whether they're spherically symmetric or not. Good. So now let's talk about big things. The big things are diagnosed by the narrow absorption component. So the line deshadowing instability and the intrinsic variability of the wind explains this small scale stuff. What about these big narrow absorption components? Well, another satellite, another era, the IUE satellite, many of you know it, used it, looked at a lot of O stars. And what they found were that these narrow absorption components exist in most of them. Probably all of them if you were able to look at all the stars all the time. So the narrow absorption components are these things down here. And they change a little bit with time. This is a range of spectral types, and they're always there. When you started looking more closely by doing time series observations, you saw that they were optical depth enhancements and that they changed in time. They evolved slowly outwards. Compare this profile with that one. So there's optical depth enhancement that slides through the line profile, but it slides through the line profile at a rate that's much slower than you would expect if it were riding on the wind. So its acceleration is a bit weird in that regard. And these so-called discrete absorption components, these things that are sliding through the line, always end up as narrow absorption components. So we think that that's actually one and the same phenomena. We just observed them at different historical epochs. We know that the narrow absorption components are ubiquitous, so we infer that discrete absorption components are also ubiquitous, although we've only really monitored heavily a handful of stars because it's very time intensive. So this is Xi-Per, one of everyone's favorite stars, and you see that it's really a pretty dramatic effect on the absorption trough of these lines. So what's going on here? Well, more monitoring. This is by Lex Kapper in multiple eras, 1987, 1980, 1989, 1991. I don't know what happened in 1990, but I guess had bad luck with the TAC that year. You see that they're always there. There's a well-defined recurrence period of a little more than 2 days, but they're not actually phase-locked between periods. So you're thinking that it might be something to do with the rotation, but if so, it's not the same phase from year to year, from observing campaign to observing campaign. So that's kind of weird. Raman Prinja made this plot, which shows that both the acceleration of the discrete absorption components, so that's how quickly they get up to the terminal velocity, and also the recurrence depends on the projected rotational velocity. So this guy sort of is taking its time, fairly low projected rotational velocity. Here, these guys in 68 Cygni get up very quickly to the terminal velocity, and there's lots of them going on. So that makes you think that it is actually tied to the rotation somehow. I know V sin I is not the rotation rate exactly. There's an inclination effect. But even so, these timescales seem to be rotated, the timescales of both the recurrence and the acceleration seem to be related to the rotation period of the star. This was shown most dramatically in a large-scale IUE program that involved a huge fraction of the community to get 15 consecutive days just banging off. There were 3 stars. Here's the data for 2 of them, an O star and a B star. And you see that there is recurrence on something that could be related to the rotational time scale. On the left, Zeta Puppis, the recurrence is about every 19 hours. The rotation period is, I don't know what it is anymore. It's very controversial at the moment. But at the time, I thought it was about 5 days. So that was a little bit hard to reconcile. The one on the right, they're coming off every 1.2 days. And we thought the rotation period was 4.8 days. So we could make some models with that. It does seem to be related to the rotation rate of the underlying star, these large-scale discrete absorption components somehow. Well, our colleagues in the solar community have known about these sorts of things for a long time. They call them co-rotating interaction regions. Have known about things that are tied to structure on the surface of the star and create perturbations in the wind. So what you need is to have an origin of fast wind next to a place on the surface of the star next to a place where a slower wind is coming out, and those will naturally interact and create great big spiral features, which is exactly what we were thinking of. So a grad student of Staniwaki's mocked this up for a hot star wind. He put a bright spot on the surface of the star, which drove more mass loss. It drove more mass more slowly than in the surrounding region of the star. So right here is the density enhanced region. Over on either side, there's less mass being driven off. And what he found was that he got beautiful spiral structures in the wind, co-rotating interaction regions, regions of enhanced density here, but more particularly regions where the velocity gradient was very, very shallow, and that, in the Sobolev approximation, also increases the optical depth that you measure. It's inversely proportional to the velocity gradient. So this is tied to the surface of the star. It rotates with the rotation rate of the star. In this case, you would see a spiral perturbation sweep by your line of sight every half cycle of the rotation. And that's pretty much what we observed. Here's what Stephen predicted from his model the variation in absorption trough of a resonance line would look like, and it looks a lot like the data that I was just showing. So, from about 1996 onwards, we were thinking that these discrete absorption components were diagnostics of large-scale structure of perturbations in the wind. Let me be clear. These are really just perturbations. The material of the wind is flowing through this spiral structure pretty much on a radial stream. It's the interaction of a stream with one set of characteristic properties here and another one here that is creating the spiral-shaped perturbation. So this doesn't actually affect the mass loss rate at all, but it affects how you interpret the line profile variations. So now we think about our standard model again just for a second and see how it's doing. We'll check in. And so we've now, from the observations, we see that sort of none of our favorite assumptions are actually completely valid. That's okay, but we have to remember that. We have to remember that. All right. So we knew about small-scale instability making small-scale structure, and we knew about co-rotating interactions making large-scale structure in the 1990s. Okay, that was a long time ago. What's happened since? And the answer is we've argued about stuff, but we haven't actually made a whole lot of progress on those things until recently. Cramner and Iwaki knew that they needed to have bright spots on the surface of an O star in order to drive more mass loss to create the big co-rotating interaction region. But there was actually no particular evidence for bright spots until last year. So here is the Bright Target Explorer. It's a nanosat. There's a suite of satellites, 6 of them, I think. 6 of them, but the one from the Canadian Space Agency called Montreal failed on launch, so there's really just 5, I think. Anyway, and what it does is it does photometry of bright stars, and it does it for a long time. So a recent graduate from the University of Montreal, Tahina Ramiara-Manatsoa, I practiced that, took this time series, 5.5 months of uninterrupted photometry. It's been binned down here so you can see stuff. 5.5 months of Zeta Puppis, one of our favorite O stars, and analyzed it. And he found a persistent 1.78 day period, which he thinks is the rotation period of the star. And in addition, there's stochastic variability. But he can analyze this now using pretty standard techniques of looking for star spot distributions, modeling a distribution of light on the surface of a star in terms of bright or dark spots. And what he finds with Zeta Puppis is that there are bright star spots there. So the panel on the left here is very interesting. It shows at different epochs, so he divides his 5.5 months up into different intervals. And there's always a 1.78 day period, but the morphology of the light curve changes as time goes on. So that means the spot distribution on the star changes. And so he has 2 different representations of that here. But this is at the same phase always, but you see the spots have moved around. So that's really interesting, because that means the spots are not localized on the surface of, well, they're localized at an era on the surface of the star, but they can move. And that's interesting. This is exactly what we need to explain these discrete absorption components. We need something that's always there. There are always bright spots there, but they're not phase locked. They drift with time, so that if what we see in 1990, what Lex Kapper saw in 1990 was different from what he saw. Qualitatively looked the same, but it wasn't phase locked with what he saw in 1988. So that's really interesting. We now have evidence for bright spots on the surface of O stars, although some people disagree. So this is very new, and there's different interpretations are possible. So there's a bit of arm wrestling going on in the community right now as to what this 1.78 day period really is. Is it really the rotation period? That's actually a little bit fast, so interesting, could be interesting. And whether this is really tied to the origin of discrete absorption components remains to be seen. We're not quite there yet. But this is a case of a prediction from theory that finally gets some sort of observational evidence for, and so we're making progress. There are many other questions that come up about O stars. O stars are actually not really well understood. There's lots of things that we need to study. For example, why are there bright spots on the surface of O stars? Well, Cantiello and Braithwaite think that a subsurface convective zone might be able to produce magnetic fields that can buoyantly be lifted up to the surface of the star. In doing so, they provide a little bit of pressure support so that the observer on the outside is actually seeing a deeper layer than they otherwise would, and that would be a bright spot. That might be an explanation. Something that has worried me for a very long time is whether the discrete absorption components, if they're caused by co-rotating interaction regions, which do have velocity gradients in them, if those can survive in the presence of this instability, the line deshadowing instability that just shreds the wind. And very recently, Sundqvist and Owocki and Pols have been doing the first 2D simulations of the instability, which is very computationally challenging. And the interesting thing that I noted was that they are finding that the instability-driven density enhancements go right down to the surface of the star, so that even if there were fast wind, slow wind at the surface of the star, it looks like it might persist through all this generation of small-scale structure. So it looks like the problem of having large and small-scale structure might not be as severe as I've been worrying about for a long time, which is great. But there's much more work to be done, and we're now talking about multi-dimensional, time-dependent radiative transfer. So that's certainly a problem for people smarter than me. But let's, at the end of my story here, let's see where we've been. We started in the 1960s with O stars being kind of boring, just sitting there. And now we've got a very different picture of them. We know they have radiatively driven outflows. That's not controversial. We know they're intrinsically unstable, and that has lots of observational consequences. Non-monotonic velocity laws, inhomogeneities, all of which affect our diagnostics of the mass loss rate, which we want to know ultimately what is the mass loss rate, because then we want to know how that is affecting the surrounding environment of the star and how that actually affects the evolution of the star as well. So those are interesting things. We also know the winds are structured on large scales. In Tahina's image here, you see both clumping, random clumping here, that's small scale, and you see the co-rotating interaction region coming off from the bright spot on the star. So the O stars, the surface of O stars, are no longer just radiatively in radiative equilibrium. There's much more going on the surface of these stars than we thought. And that's interesting. So O stars are very, very timely, very topical. And I wanted to close by expressing my sincere gratitude to colleagues here at the IAC for making huge amounts of data available to the community, because that is having many different eyes look at the data and try to sort out what's going on is exactly what we need right now to feed the next generation of theory and observation and theory. This is, I think I'm supposed to say this IACOB, but I know that everyone says Jakob. And when I think of Jakob, I remember old stories about ladders going upward. And so I think this is how we will make progress, going up Jakob's ladder with theory and observation, and eventually we'll get to some point where we can look down and say, aha, I understand what's going on. And I would certainly welcome that day. So thank you very much.
Thank you very much. Questions?
Hello, thanks for the conference. It was pretty illustrative. Do you have nice pictures of OB stars with nice nebula around, showing some of those beautiful spiral wind structure? I mean, can this have a counterpart in really optical images or ultraviolet images of the stars?
So the question I think is, can we actually image the spiral structures? Has it an effect on the nebulae? So far, I think the answer is we don't know. I would certainly like to be able to image them. I think that with our advances in interferometric imaging, there's a chance for the nearest O stars we might be able to see it. But I don't think we've been able to see any consequences on the larger scale H2 regions or nebula around, at least not yet. That might be partly because there are many rotational cycles will typically go on, and it kind of averages out probably. But it would be great to have some sort of independent confirmation of these structures as well, instead of the spectroscopic inferences that we're making.
A reminder, people watching online, they can send questions through email.
So, after all these complications, could you say something about the mass loss rate?
Right. So, we can always say something. But if you want the right answer, then that costs more, as always. So what has happened? So at the beginning of this, we had mass loss rates predicted by the modified Castor-Abbott-Klein theory. And what has happened, the net result of all this structure and interpreting diagnostics, is that the mass loss rates predicted in the early 1990s have come down by maybe a factor of 3-ish. So if the original prediction was that it was 3 times 10 to the minus 6, now it's 1 times 10 to the minus 6. And so that affects solar masses per year. So that affects things a little bit, but not actually as incredibly much as you might imagine. So it loses a little bit less mass than per year, so its evolutionary changes are a little bit slower, and so on and so forth. But this is the values have bounced around quite a lot by an order of magnitude, but we're kind of coming down to a middle range between the highest and the lowest part of the bounce. Joachim, would you agree with that?
On the numbers, yes, but I think the consequences are more dramatic than you are saying. A factor 3 in stellar evolution is a lot.
Okay.
So we have, when we would compare the stellar evolution in the 90s to the present day stellar evolution, we would see a lot of effects if these people would account for this factor of 3. And the point is that the people have still not, I would say so the people have not taken the observation seriously, the people who are doing stellar evolution. So they are still using the mass loss rates which were from our years 1990. So all this takes always time.
It's the other guys though, right?
More questions?
Thanks for the talk. Do we have an idea of what pulsations and magnetic fields can affect all these structures and these?
So that's a really interesting question. I focused on the bright spots here, but as you know, as you've shown, the O stars are also the home to pulsations, non-radial pulsations, probably many modes of them. Pulsations also provide heating. They provide of the layers of the atmosphere. They can provide a hot spot too that doesn't stay fixed on the surface. So I think that is another possible mechanism for initiating fast wind, slow wind, and therefore co-rotating interaction regions. The spots are a little bit preferred right now, partly because in the intervening years, something I spoke about not at all, it has been the detection of magnetic fields on the surface of O stars as well. So in our minds, when we think about magnetic fields, we think about star spots. That may or may not be the right thing. But we now know that there are also magnetic regions in O stars, and that could be another part of the hot spot idea. The magnetic fields also create an entirely new structure around the stellar wind. It's no longer stellar wind, it's a stellar magnetosphere, and that's extremely interesting, but a whole separate topic. It's not so much mass loss then as mass recycling around dipolar fields, and has very interesting consequences, but it's different from the wind. And it's only 10% of the O stars we seem to think have really big magnetic fields. So all this is, I think, just goes the direction of making O stars much more interesting than they were thought of
Things
when
can-
I was a
Yeah, things can become even more complex in all this.
Yes,
yeah.
yes. Complexity is interesting because it tells us something. It's trying to tell us something.
Can you comment on the interaction of the wind with the potential protoplanetary disks around these stars?
Interesting. So I would, actually I can't really comment on that because I don't know anything about it. I would guess that the wind, the mass loss rates here are very large compared with Herbig AE, BE stars. And so, so I would think that, that this will tend to disrupt a protoplanetary disk around, around, if it exists around a massive star. What this structure would do to it, I don't really have any idea. But it would, yeah, I think it would not be good for the protoplanetary disk. But I'm not, to be honest, I'm not well informed about the existence of such structures around massive stars. I'm sure they exist, or that some sort of disk-like structure exists around early type stars, but forming early type stars. But I know nothing about it.
There are some cases, Perseus, for instance, for some bright stars and some of the most luminous stars in Perseus, for instance, have been it has been proposed that there are protoplanetary disks around them.
Yeah.
I wonder whether the interaction of the winds may play a role in this.
I'm
That was
sure they would.
the basis for the question.
I'm sure they would play a disruptive role, but beyond that, I can't say.
If individual stars are so difficult to understand, the integrated light of galaxies is even more difficult. So, what are the consequences of the evolution? I mean, all these studies on luminous UV galaxies, for
Right. So
instance.
that's a really interesting question. It may not be so bad because if you're looking at an integrated population of massive stars, as you typically do whenever you get out very far, you're looking at a cluster of young stars and you're not resolving them. I think that there will be a lot of averaging over all these kinds of things. So the fact you would probably, if you're measuring feedback, it would be good to know feedback from the unresolved cluster. It would be good to know that the mass loss rate, the rate of feedback is smaller than we thought 20 years ago. But apart from that, I think that many of the consequences would be quite similar. So it may not be as dramatic. Again, the evolution of the stars would be over a somewhat longer time scale, but so age determination might change. But the details of the structure of the wind probably don't matter on that scale.
Okay. Thank you.
Any other question?
Very short one. Will the James Webb contribute to understand a bit more the picture of massive stars?
I'm sorry, with James Webb?
The James Webb, yeah.
Yes. So my bias is to talk about UV resonance lines and that sort of thing. So James Webb won't help a lot with that. But there are some other mysteries of mass loss rate, trying to increase the precision a little bit more, that access to the infrared will help with a lot, just to discriminate between, try to determine the mass loss rates better than a factor of 3. I think it'll help there. James Webb, for the galactic stars that I've been talking about, James Webb is not great because it's too sensitive. And the spectral resolving power is a little lower than you might like, but where the big advantages of James Webb are going to come in has to do with star formation, I think, and looking in obscured environments, and probably also exploring disks around forming stars. I think that's where a lot of the stellar aspects of James Webb will really, the contributions to stellar astrophysics of James Webb will really happen, besides everything else, like exoplanets and the edge of the universe and those things.
Any other question? Let me check. I remind you that we have now the colloquium coffee, and we don't have any further questions. So thank you very much again for the nice talk.
Thank you.